Hello, this little video is about the Galois group of a polynomial of degree 4, quartic. It will be using the trick of the resultant cubic, a cubic polynomial associated naturally to a polynomial of degree 4. Let me start with a monic polynomial of degree 4. Assuming that its coefficients are taken from some field k. K will be this basic field. So in the splitting algebra of this polynomial, which is an algebra extending the field k, the commutative one, I'll have the factorization to the linear terms. So that is in the splitting algebra. That is the meaning of the splitting algebra. And what we can do in degree 4 is we can turn this polynomial into something which is of degree 3, called the resultant cubic. And again, it's easier to say what is the complete factorization in the corresponding splitting algebra. So it will have 3 roots in the splitting algebra, and the roots are related to the original roots of f via these procedures. Take a pair of roots, take another pair of roots, take the sum. And you could do it in 3 ways, hence the 3 roots. You get up, sorry, it's x1, x3, say x2, x4, and the last x1, x2, x3, x4. Sorry, x4 and x2, x3. So that is our rewriting rule, turning roots of the original quartic into 3 roots of the new cubic, and then we could see what happens with the coefficients, what the coefficients should be if we have such factorization. The coefficients are computed in some other video. To be this. And again, it's just some algebraic combinations of original coefficients, so still be a polynomial with coefficients in our base field k. So the key ingredient, key trick in what happens is the following observation. So this splitting algebra of G is naturally subalgebra of the splitting algebra of F, since we can interpret all the roots as algebraic combinations of the original roots. Why this formula? So we have this embedding of commutative algebras. By the design, the symmetric group on 4 elements on these 4 roots acts naturally on the algebra, and restricted this action preserves the subalgebra, and actually the homomorphism of the group from the group S4 into the group acting in here will be just this homomorphism into the group S3, I'll call it phi, which really just records how we permute this 3 algebraic expression of x's. So the key fact which is going to be used is about the building blocks of these algebras. These are commutative algebras, and they're separable away from characteristic 2, and so they're direct sums of fields, and actually this is just all the same field in the direct sum. Depending on how many copies, it still be the same field. So this is what is called the splitting field, and I'll call the splitting field of G L, and that F, the largest, will be the splitting field of the original F. So I'm interested in the splitting field, but I'm particularly interested in the symmetry group of this field, in the Galois group of the polynomial. And the possibilities are limited. So first is a subgroup of the symmetry group S4, this Galois group, or the Galois group of the polynomial, and second it's supposed to be transitive subgroup. So using group theory we could list them all. That will be my first column in the table of answers. So it could be the whole group S4, it could be the alternating group A4, dihedral group D4, cyclic group generated by the longest cycle permuting all 4 elements, and then the Klein subgroup V4. So that is the complete list of transitive subgroups. And the key fact, which I still hasn't mentioned yet, is that this homomorphism restricting the symmetry group action on the splitting algebra of F to the symmetry group S3 action on the splitting algebra of G is nicely aligned with the Galois groups of my splitting fields. So namely the fact is that if I apply this to the Galois group of polynomial F, which is the Galois group of automorphism group of this big extension, we will get the Galois group of the polynomial G, which is the automorphism group of this extension. So we could immediately list the answers for the Galois group of G, the resultant cubic, depending on each of the possibilities. It will be S3 in here, it will be A3 in this case. That will be restricting to a cyclic group of order 2. Again, the homomorphism is this, and it has a kernel, the Klein group before, and Klein group is a subgroup, and the quotient by the subgroup is a cyclic group for the 2. So here we still have a cyclic group for the 2, because again the intersection is of order 2 of a cyclic group for the 4 and the Klein group, and so we have to quotient by cyclic group for the 2 this one and get the answer. And here when we quotient by V4 before itself, we get just a trivial group. So these two columns give us, say, the degrees of the extensions, and that is a useful information which we can then turn to some criteria. The degree of the extension from the base field to the splitting field of G, I will list the first, and then this column will be the degree of this step in the chain. It will be the degree of this extension, extending splitting field of G to the splitting field of F. So here this degree is the same as the size, is the order of the Galois group. This is just the degree of the splitting field of G, and it must be equal to the symmetry group order. So we'll have 6 here, we'll have 3, I'll have 2, we'll have 2, and we'll have 1. And this we can really recompute by knowing that the total degree has to be equal to the order of this symmetry group. So the answer here is the order divided by the order. So it is the index of the pair. And it is 4, and it's 4 again, and it's 4 again, and it's 4 as well, and the only place where it drops down to 2 is in here. And so we have an answer, somewhat useful answer in terms of these degrees of which symmetry group, of which Galois group we're looking at. So let's try and really unpack these answers a little bit. So in the first two cases, when the degree of the splitting field of our resultant cubic is 6 or 3, we can be sure that this cubic G is irreducible. And we can separate between these two cases by using the discriminant criterion for when the symmetry group is one or the other for an irreducible cubic. So the criterion says that the discriminant of this resultant cubic has to be a square in the coefficients for the symmetry group to be in the alternating group A3, and otherwise it is not A3, so it must be the full S3. The discriminant of the resultant cubic is the same as the discriminant of the original polynomial, so you could really say that the first case is a special, the discriminant of the original polynomial should not be a square. All other cases will be having this discriminant being a square. So let's look at the other possibilities. So the next two possibilities say that the degree of the splitting field of the resultant cubic is 2. So G cannot be irreducible. It has to be reducible into something which has exactly one root, and then the other factor will be an irreducible quadratic, and it will have the symmetry group as it should, cyclic group for the two. So G in these two cases has just one root. And the last case is when the degree of the splitting field of G is 1, and that is only possible when the resultant cubic completely splits over the base field. Has all the roots in the base fields, all its roots in the base field. So this is a characterization in the sense of when do we have each particular answer for the Galois group depending on the resultant cubic and the original polynomial as well. Some applications of this are to come. See you later.